Welcome to The Explainer. Today, we're unpacking the massive, totally invisible forces acting on our industrial infrastructure. We're going to look specifically at one seemingly simple component that actually holds these rigid systems together, and what happens when critical structural engineering parameters are just ignored.
I mean, it sounds completely impossible, right? How in the world can a tiny 1 millimeter mistake take down a massive 20-inch steel pipeline? It's a question that literally keeps piping engineers awake at night. Well, today we're going to solve that mystery. We're going to see how a tiny gap, or rather the lack of one, can lead to a catastrophic blowout, and how understanding just a little bit of installation philosophy can prevent an absolute disaster.
Okay, let's dive into this. Here's our roadmap for today. First, we'll meet the rubber bellow. Then, we'll check out the FSA design standards. After that, saving the pump nozzle, avoiding the pressure thrust trap, and finally, preventing those pesky installation leaks. Let's get to it.
Section 1. Meet the rubber bellow, the flexible hero of industrial piping.
So these bellows are designed to safely handle non-critical services. Think water or air systems up to 10 bar gauge and 100 degrees Celsius. Basically, they're engineered to move exactly where rigid steels simply can't. In these heavy-duty systems, a rubber bellow is like a massive shock absorber. It handles 5 specific types of movement. It stretches out, which is axial extension. It can squeeze together, or axial compression. It slides side to side for lateral deflection. It bends to absorb angular movement. And it can even handle torsional movement, which is twisting. It is literally a dynamic, flexible bridge dropped right into the middle of totally unyielding steel pipelines.
Moving on to Section 2, the FSA design standards, the ultimate rulebook for flexible piping. Now, engineers can't just cross their fingers and guess how far a piece of rubber will stretch before it tears. I mean, that would be incredibly dangerous. Everything about these components is strictly governed by the FSA, the Fluid Sealing Association. They are the governing body that sets the technical requirements and exact design details for all non-metallic and rubber bellows. So, when a manufacturer builds one of these, they aren't just winging it as they go. They are strictly following the FSA's parameters for face-to-face dimensions, spring rates, and allowable movements.
To see just how precise we're talking, let's look at a standard 4-inch joint. The nominal face-to-face length has to be exactly 150 millimeters. Axial compression, capped right at 19 millimeters, while extension is strictly limited to 11 millimeters. It handles exactly 16 millimeters of lateral deflection and exactly 9.4 degrees of angular movement. By specifying a bellows size, design pressure, and temperature according to these FPSA standards, piping engineers ensure their systems operate safely within absolute known limits.
Section 3. Saving the pump nozzle. Why we actually need this flexibility. I mean, why do we even insert a flexible rubber piece into a massive, heavy-duty steel pipeline in the first place? What exactly are we trying to save here?
Picture this. You're trying to perfectly align heavy underground steel pipes with a brand new industrial cooling water pump. Getting that alignment down to absolutely 0 millimeters of error? It's pretty much impossible. You're always going to have a slight piping misalignment, maybe just 5 to 10 millimeters, either axially or laterally. Now, if you take heavy steel bolts and force those misaligned flanges directly onto the pump, you are going to transfer a massive amount of mechanical stress right into the pump's nozzle. Over time, or honestly even immediately, that stress will literally crack the pump casing. So, we install the rubber bellow first. It easily absorbs that 5 to 10 millimeter misalignment, leaving that really expensive pump nozzle completely load-free.
Section 4. The pressure thrust trap, the invisible force waiting to strike.
Okay, take a look at this staggering number. 19,625 kilograms. That is nearly 20 tons of force. So where does all that come from? Well, if you have a 20-inch pipeline, so a 500 millimeter internal diameter, operating at just 10 bar of internal pressure, the physics of that water pushing outward generates a massive axial load across the pipe. That's almost 20 tons of pressure thrust actively trying to push those pipe ends apart.
And if that 20-ton force hits a flexible rubber bellow unrestrained, the results are an absolute disaster. Our source material gives us a very direct warning here. Quote, "If we do not keep the tie rod nuts tight, this huge pressure thrust will transmit to the piping system and the bellow will axially overexpand and fail." There are actual documented cases where massive 24-inch bellows have literally exploded. Why? Because the heavy steel tie rods spanning across the bellow were either missing entirely or the nuts were just left loose. Without those rods to hold back the immense pressure thrust, the rubber just stretches right past its FSA limits and blows out.
Section 5. Preventing installation leaks. Bolting it down the right way.
Now, while a huge explosion is obviously the worst-case scenario, engineers also constantly battle with persistent water leaks just from improper bolting. Let's look at the structural difference here. Those tie rods we just talked about? They're held in place by metal brackets called stretcher plates. The absolute wrong way to install these plates is inside the retainer ring, resting directly against the soft rubber of the bellow. If you do it that way, when you tighten down the heavy tie rod nuts, the stretcher plate pulls inward, squishing the soft rubber and actually pulling the retainer ring loose. You just end up with a continuous water leak that you can't stop. The right way, and really the only way, is to bolt those stretcher plates strictly outside the rigid metallic flanges of the pipeline. The metal flange is stiff, it won't budge, and your rubber seal stays perfectly tight.
So, putting all of this together requires a very specific, careful sequence. Step 1. You install the bellow to absorb that 5 to 10 millimeters of initial misalignment we talked about, keeping the pump completely load-free. Step 2. Tighten all the main piping joints securely. And Step 3. This is the real magic right here. You tighten the tie rod nuts, leaving a maximum gap of exactly 1 millimeter. By leaving just 1 millimeter of play, the bellow can still absorb tiny vibrations. But the second that 20-ton pressure thrust tries to expand the pipe, it instantly hits those tight tie rods. The steel rods take the massive load instead of the rubber, and the whole system runs perfectly safely.
It kind of changes how you look at the engineered world around you, doesn't it? Next time you happen to walk past a massive industrial pump facility or a water treatment plant, take a really close look at the piping. Will you be able to spot that tiny 1 millimeter gap on the tie rods? Just remember, that tiny, deliberate space, combined with perfectly placed stretcher plates, is exactly what's saving that heavy industrial infrastructure from catastrophic destruction every single day. Thanks for joining me on this explainer, and keep your eyes open to the incredible hidden engineering all around us.